The experiment is very, very simple. We just need a very, very small hole, and we need a reservoir, and we just have to let the superfluid go through the tiny, tiny hole, and then we count the atoms, just like we would count a current, measure a current in an electrical circuit. The challenge here was to fabricate a very small hole, a single one, which was about only 30 to 40 atoms across, and for that we needed actually very sophisticated tools from nanotechnology to fabricate the holes and then be able to seal it, cool it, and be able to detect the flow. It took us more than 100 trials, maybe 200 too, before we succeeded at it. The hole is so small that any impurity actually will potentially clog or block the hole. So the whole challenge has been actually to keep the hole open, and after that, at low temperature, to be able to perform the measurement. We solved the problem by chance with my great student, Pierre-François, who at some point deviated from the procedure, and it turns out that he left the flow going on while we were cooling the apparatus. And it turns out, just like a river won't freeze because of the energy at during the winter, it is the same here. The hole stayed open because there was always something going through it. Now we know this is the key thing, and this is what we will always do now. Many groups around the world have explored the possibility of using this superfluid helium, since it has no viscosity, as a very efficient rotation sensor. So we could imagine these rotation sensors to be put in space or in anywhere that is needed to actually detect very small rotation. And if we can do it very small, it would become much more practical, because it would be easy to actually launch it, it would be easy to transport, it would be easy for just about anybody that has a need if it can be developed on a chip. In order for so to happen, it is necessary that we understand the physics behind the flow in very small channels.